Hello, and thank you for joining us. Today's webinar is Improved Detection of Regulated Elements in Toy Products Using Ultrasonic Nebulization with ICP-OES Detection, presented by Fred Smith, Technical Product Manager for Teledyne CETAC. If you have any questions, please feel free to submit the questions during the presentation using the question function, and Fred will respond via email after the webinar has concluded. This webinar is being recorded and will be available within a few days. Okay, I'm going to turn it over to our presenter, Fred Smith.
Thank you very much for the introduction, Shelley, and thank you everyone for attending today. Today's topic is a quite interesting topic, especially as we approach the holiday season, and that's improved detection of regulated elements in toy products using ultrasonic nebulization with ICP-OES detection. And this concerns the European standard EN71. EN71 specifies a range of safety requirements for all toy products sold in the European Union. There are a total of 14 parts to EN71. And a couple of the first examples include Part 1, which is mechanical and physical properties. And examples might be a sharp edge or point on a toy product, or small parts that could come off and be swallowed by a child. Another is Part 2, flammability. Highly flammable solid materials that could occur in certain items, such as play costumes that children might wear. The particular part we're interested in today's webinar is EN71 Part 3, and that concerns the migration of certain elements from toy products that could be placed in the mouth by children. The elements of interest are listed below, and there are a total of 17, including chromium-3 and chromium-6 and organotin. Okay? Compliance with these EN71 limits is required, again, for all toy products sold in the EU. Example, toy components could include polymers, paint, and fibers. There are 3 categories of toy products that are concerned in EN71 Part 3. Category 1 include dry, brittle, powder-like, or pliable materials such as chalk, crayons, or modeling dough. Category 2, liquid or sticky materials such as bubble solution, finger paints, liquid adhesives, glue sticks, and slime. Category 3 is the category we're going to be concerned about today in the webinar, and these concern scraped off materials such as hard and soft plastics, wood, textiles such as fibers, paint coatings, and glass and metals. Again, I did note this in the earlier slide. This particular study does not include speciation of chromium-3 and 6. The chromium is reported as total chromium, and organotin compounds were not measured, but that is also part of EN71 Part 3. Okay. So the accessory we are going to look at today is an ultrasonic nebulizer, and that's an accessory for ICP optical that enables higher sample transport efficiency versus a standard pneumatic nebulizer to the plasma. This particular accessory's benefit can be helpful for detection of more difficult elements such as arsenic, lead, antimony, and selenium when using ICP-OES for detection. And this webinar will describe the method used for both sample preparation and the use of the ultrasonic nebulizer in the detection of trace elements in toy products per EN71 Part 3 criteria. So again, the principle of operation of an ultrasonic nebulizer is that in place of a regulated gas flow for generation of a liquid sample aerosol, such as from a pneumatic nebulizer, the liquid sample is pumped across a quartz plate, and underneath that plate is an oscillating piezoelectric crystal. Those oscillations couple through the quartz plate and break up the liquid solution into an aerosol. Ultrasonic nebulization is typically up to 10 times more efficient versus a conventional pneumatic nebulizer, and hence that should impart us greater sensitivity and lower detection limits. Here is a front view, and we'll actually see pictures of this in the laboratory setting, but this gives you an idea of the dimensions and, of course, the weight of the system. It is essentially a benchtop system or a system that can be easily placed on a laboratory cart and then connected to the host ICP-OES. Two important features that I do want to mention about the ultrasonic nebulizer is it does have an integrated desolvation system, which is electrothermally cooled, so there's no recirculating cooling liquid necessary. This removes excess sample aerosol solvent to ensure plasma stability. It also has a built-in drain peristaltic pump mounted on the back panel of the unit. That removes any condensed sample solvent to waste. That peristaltic pump is not used to move sample liquid to the nebulizer. You would typically use the host peristaltic pump that is from the ICP, which is normally under computer control of the ICP software. And you would use that pump, like with the standard nebulizer, to move sample liquid to the ultrasonic. Again, this drain pump is simply there to remove excess condensate. I will move back one slide. I will mention the two temperature controllers on the front of the unit. Those are factory set at 140 degrees C for a heater and 3 degrees C for the electrothermal condenser. The higher temperature, of course, is used to keep the generated aerosol in a vapor phase. 3 degrees C, just above the freezing point of water, is used to condense out excess sample solvent to ensure plasma stability. Okay. So a schematic of the internal workings of the ultrasonic nebulizer. The area in red is heated, and that's under control of one of the temp controllers. That's what's heated up to 140 degrees C. And then the condenser, and that is usually for water-based samples kept at 3 degrees C to remove excess sample solvent. So what then goes to the ICP is essentially a dry sample aerosol of salt particles. Okay. I will also point out to the bottom left of the schematic where it says argon in or AR in. That is where a flow of gas from the host ICP will come in. And in this case, it's acting as a pure carrier gas. It'll simply remove and sweep out the generated aerosol and send it through the desolvation apparatus and then to the ICP. It does not generate any aerosol as with a conventional pneumatic nebulizer. The piezoelectric crystal, which vibrates, will be doing that task. Here is a close-up of the transducer, which actually generates the aerosol. The piezoelectric crystal is sort of a tan-colored disc, and that's pointed out by the green arrow. Mounted on top of that is a quartz faceplate, and the sample solution will then be pumped and flow across that plate. And as the vibrations are coupled from the piezoelectric crystal through the quartz, the aerosol is then generated. Again, the argon nebulizer gas supply from the host ICP would only be used to carry or sweep that through the ultrasonic nebulizer and then to the ICP. That gas flow in this case does not generate the aerosol. So, instrumentation and labware then used in this study. We used a PerkinElmer Optima 5300 DV ICP-OES. The ultrasonic nebulizer, again from Teledyne CETAC, is the U5000 AT Plus model. For sample preparation, we used a block digestion system from SCP Science. And then in particular labware that we used digestion tubes for the hot block. These were 50 ml polypropylene vials that were flat bottom. And we also had to use syringes and filters, and these were needed to filter out any textile fibers and any paint flakes from the samples that we were going to prepare. Then reagents. So there's detail here that we will then go through in some upcoming slides, we used a higher purity grade of hydrochloric acid, also hydrogen peroxide, single element standards, and in particular, we used 2 reagents, and these reagents are added to our diluent solutions for both standards and samples. One is mannitol, which is a higher molecular weight sugar, and L-Cysteine, which is an amino acid. And we'll get into details on why these are used. So here is a picture of the ICP-OES instrument that was used in the study. This is the PerkinElmer Optima 5300 DV. Next to it is an example of one of the auto samplers also available from Teledyne CETAC to automate the method. That's an ASX560, but that gives you an idea of the dimensions of the equipment that's used. Okay. So opening up the side door, here you see the conventional nebulizer and spray chamber used with the Optima 5300 system, and directly below it you see the built-in peristaltic pump that is under computer control of the system. That is the pump, of course, that will also use to send sample solution to the ultrasonic nebulizer. And here then is the picture of the ultrasonic nebulizer attached as an accessory to the ICP-OES. Notice that in this case, the standard nebulizer and spray chamber have been removed. It only takes a few minutes to detach, and we used an interface kit with a gas inline and a sample outline to connect to the host ICP. Again, the peristaltic pump to the left is what's used to send the sample solution to the ultrasonic nebulizer. Here is a picture showing connection to another PerkinElmer ICP-OES. This is a contemporary model, an Avio 500 series. Again, we've placed on a laboratory cart, and you see next to it on the right is an auto sampler, in this case an ASX280, and in the middle of the picture, it's hard to see the details, but the built-in peristaltic pump on the host ICP, again, is used to move sample from the auto sampler to an ultrasonic nebulizer. This is just an example showing it on the current model, but the data collected was on an Optima 5300. So here is a close-up of what the aerosol looks like. And I've pointed out, again, with the colored callouts, there you see the transducer mounted on the ultrasonic nebulizer, the sample inlet line, which is a line of PEEK tubing that would connect to the outlet from the peristaltic pump, with the other end, of course, if needed, attached to an auto sampler. And then in the conical spray chamber, you see the actual aerosol being generated. You can see it's a thick and heavy aerosol because of the efficiency of the ultrasonic nebulizer. Just to the left of the yellow arrow, you do see a port, and that port at the top of the spray chamber, that is where the aerosol, the transducer is doing that task. Again, to the bottom of the spray chamber, just to the right of the red arrow, you do see a drain, and that, of course, is excess sample solvent that's being drained away by a small peristaltic pump mounted on the back of the ultrasonic nebulizer. Okay. And here is a very short video just showing the one-button operation. Okay. So once you have everything connected and the solution is flowing, you simply press the yellow operate button, and that's all that's done to generate the aerosol. Okay. So the toy products we're actually looking at then in this particular study, and these were all Category 3 types. These were purchased at a local store, included wooden blocks, in particular paint that we can scrape off the blocks, so essentially paint flakes, plastic stacking rings, and a fake mustache. This would be something that would then come under the realm of a costume that children might use for play. So the leaching solution we're going to use is 0.07 molar HCl made from a high purity grade, warmed to 37 degrees C, and that is used to simulate gastric fluid and the migration of trace elements from these toy-related samples into the human body after swallowing. So the first sample, a plastic stacking ring, we actually picked a green one. The other colors were shown in the previous slide, but 3 samples were cut with a fresh razor blade, and the masses are given there. 2 samples were added to individual pre-cleaned 50 milliliter polypropylene vials, and 1 sample to a borosilicate glass vial. We did mercury separately so we could keep mercury stabilized in glass. So we will have a separate sample and a separate calibration for mercury. Boron and the other 15 elements were done in the polypropylene vials, but especially to keep lower levels of mercury, which might occur stable, we did that in borosilicate glass. The same done with the fake mustache fiber. 3 samples were trimmed with the scissors, and there are the masses given. Again, 2 samples each into individual polypropylene vials and 1 sample to a borosilicate glass vial. And finally, red paint from wooden blocks, and these were carefully scraped using the edge of a sharp razor blade. We got samples all right around 0.1 grams. It took a while to get enough material scraped off. And again, 2 samples to 50 ml polypropylene vials and 1 sample to a borosilicate glass vial. Now, the hydrochloric acid solutions, I did mention the leaching solution being 0.07 molar HCl. Of course, the calibration standards were also made up in 0.07 molar HCl, but we did add some additional reagents. Okay, first one is hydrogen peroxide. That alleviates arsenic species transport effects by oxidizing all of the arsenic to the arsenic 3 state or arsenate. That gives more uniform transport and signal for arsenic. Then the L-Cysteine. L-Cysteine is added to improve mercury transport and washout, and mannitol is added to improve boron washout. And we'll look at the structures of both those compounds in just a moment. Okay. So for the 3 example samples, 1 replicate sample, as I mentioned, was for mercury, 1 replicate sample for boron, and 1 replicate sample for the other 15 elements. Again, mercury done in borosilicate glass to help with stabilization. A solution mass of about 100 times the sample weight was added to each red paint flake sample. A solution mass of about 50 times the sample weight was added to each stacking ring and fake mustache fiber sample. Now, the sample vials were then placed in the block digestion system at 37 degrees C for 1 hour in darkness with manual agitation about every 2 minutes, followed by another hour at 37 degrees C in darkness with no agitation. The samples that contained the paint flakes and the fibers from the fake mustache were then carefully filtered with the 10 ml syringe and the 0.45 micron filters to remove that material. So, of course, we didn't have that in the final solution. So here is a picture of one of the digests, and that was one section of the green stacking ring, and I believe it was around 15 mLs of leaching solution that was added, and that went through the procedure at 37 degrees C for an hour with agitation and for an hour without agitation. Now, standards preparation. So 1 set of calibration standards containing 20, 50, 100, and 200 microgram per liter, or ppb, of those 15 elements. Those were prepared in 0.07 molar HCl with 0.4% hydrogen peroxide using pre-cleaned 125 milliliter low-density polyethylene, or LDPE, bottles. The next set of standards contained, again, the same concentration range, 20, 50, 100, and 200 ppb boron. Again, these standards are prepared in 0.07 molar HCl with 0.2% mannitol. That, again, was also done in pre-cleaned 125 ml low-density polyethylene bottles. Okay. And here I want to point out the structure of mannitol. It is a sugar, and it contains cis or gem-diol hydroxy groups. Those hydroxy groups are what can bind boron, typically as boric acid or borate in solution. So this is used to stabilize the boron and to help with boron rinse in and wash out. Then finally, the third set of standards containing, again, 20, 50, 100, and 200 microgram per liter mercury. The standards were again prepared in 0.07 molar HCl, but with the addition of L-Cysteine. And this was done in pre-cleaned 100 ml borosilicate volumetric flasks. Again, switching from polymer vessels to glass to stabilize mercury, especially lower levels of mercury. And this is the structure of the L-Cysteine. What it is then complexing the mercury is the sulfur on that thiol functional group. And so this is why it's used. Again, it's to help with mercury rinse-in and wash-out in the ultrasonic nebulizer. And of course, these same reagents can be, of course, used in a standard nebulizer system for improved performance for boron and mercury. So, the installation of the ultrasonic nebulizer, you saw a picture earlier. It takes maybe 5 to 10 minutes at most. You remove the standard nebulizer and spray chamber from the host ICP. You connect a gas inlet line from the ICP-OES to the back panel of the ultrasonic nebulizer. In this case, the gas is acting simply as a carrier gas. Then you'll connect the sample outline from the ultrasonic nebulizer to the ICP torch. If you're automating this, you would simply connect the sample line from the auto sampler to the USN inlet line, connect a power cord to the USN, and turn on the unit. Wait about 10 minutes for the heater and cooler to stabilize to 140 degrees C and 3 degrees C, and then start the ICP. I showed you earlier that small video clip that has simply the one-button operation. Once the sample solutions are flowing, you simply press the yellow button and leave it on. In all of this, no computer control or software is needed for the ultrasonic nebulizer. The other things that would normally be under computer control stay under computer control, that being the host peristaltic pump that's built onto the ICP, and if in use, the auto sampler. So that doesn't change. The ultrasonic nebulizer is just another accessory through which to pump sample solution. Operating conditions, as you'll see, the one I will point out that may need to be adjusted is just the nebulizer gas. For a standard nebulizer system, like a standard glass concentric nebulizer, that may be around 0.6 to 0.65 liter per minute. With the ultrasonic nebulizer, it's often a little bit lower. In this case, it was 0.55. But all of the other conditions, ICP power, plasma gas, auxiliary gas, resolution, integration times, sample uptake rate, all remain pretty much the same. So typically, only the nebulizer gas may have to be adjusted, which is easily done and then saved in a method in the computer software. So, calibration, reagent blanks and standards. Reagent blanks simply follow the same diluent solutions, the 0.07 molar HCl with 0.4% hydrogen peroxide, the HCl with the mannitol, and the HCl with the L-Cysteine. And again, the amounts of these added reagents aren't very much, so you don't have to use a lot. 3 sets of standards for 3 separate calibration curves, one for boron, one for mercury, and one for the other 15 elements. No internal standards were used. In particular, we wanted to look at the effects of using the mannitol and the L-Cysteine on the calibration. So calibration coefficients, typically you will look for a minimum of 2 nines 5, preferably 3 nines or better for your calibration curves. I pointed out in the blue for boron and the red for mercury, the excellent correlation coefficients obtained when we use the added mannitol and the L-Cysteine. That helps considerably to ensure you rinse through between the standards and you don't have memory effects that can then skew the curves. The other elements all come in. The range of the correlation coefficients range from, I believe, 3 nines 4 to 4 nines. So calibrations were certainly calibration curves were certainly satisfactory. Okay. So first, we wanted to look at both instrument detection limits, or IDLs, and then limits of quantitation when using this method. The reagent blanks were measured 10 times as a sample. The individual IDL is defined as 3 times the standard deviation of the reagent blank concentration. Okay. We were also more interested, though, in the limits of quantitation. The LOQ is defined as 10 times the standard deviation of the reagent blank concentrations. And again, the reagent blanks listed below, the 0.07 molar HCl with the added reagents of peroxide, mannitol, and L-Cysteine. So looking at the compilations of these detection limits, what we're trying to achieve is to get the LOQs in particular at or well below 1 part per billion, particularly for some of the more difficult to detect elements. And that we could achieve. For arsenic, we're down just below a part per billion for the LOQ. Again, not the IDL, but the LOQ. And also for lead, antimony, and a little bit higher for selenium, up around 1.6. But overall, we can push some of these detection limits quite low. And again, this is using ICP, optical emission, and no internal standard, and certainly not under clean room conditions, but using as clean reagent vessels as we could have with pre-cleaning them, and higher quality reagents such as an Optima grade or double distilled grade of HCl. So, results. First, we'll look at the green plastic ring sample. So, on the third column, you see the migration limit for a category 3. This is in milligrams per kilogram for certain elements. And you can see for some of the more toxic elements like arsenic, cadmium, mercury, and in the later slide, for lead, you will see the much lower migration limit. But in this case, for the green plastic ring, and I'll move to the next slide, I had to split these up so it's a little bit more visible. We did not detect very much coming out of that ring. And that's, again, after about a 2-hour leach at 37 degrees C. So certainly the green plastic ring did not indicate anything of an issue there. Then the fake mustache fibers. Well, then things did start to pick up a little bit. We started to see some elements come up. There we saw for aluminum, a little bit for chromium, and a little bit coming up again above the background spectrum for some of the elements of note, but again, nothing very large from the leaching of the fibers. And then finally, the red paint that was carefully scraped off the wooden block. Here we did see some of the levels start to creep up. There you see for aluminum, barium in this instance. Again, nothing detected for anything like arsenic, a little bit for cadmium, but well below the migration limit. But others started to come up here with the paint: manganese, tin, strontium, zinc, but again, all well below the migration limit. So for the ultrasonic nebulizer itself, there are two voltage setups, one for 115 volt, and there's the part number for it, and one for 220 volt. They're hardwired depending upon the voltage in the country you are using the system. So you would order an A plus for 115 volt, a B plus for 220 volt. A common question then is interfacing to a host ICP-OES. We have interface kits for all of the models that are currently on the market: Agilent, Analytic Jena, Perkin-Elmer, Shimadzu, Spectro, Teledyne Lehman, Thermo Fisher. These are all available. So one interface kit is provided at no charge with each U5000 AT+. You would simply need to specify which model ICP you have, and then the correct kit could then be sourced and placed with the shipment. Other application notes: this one in particular was for the toy product safety EN71, but this accessory coupled with ICP-OES is used across a variety of applications. We did a recent webinar on municipal water per US EPA method 200.7. That was a treated water sample, well water, untreated. Pharmaceuticals per USP 232-233, we looked at aspirin. Food matrices and juices, which has been a very important topic, particularly when looking at arsenic. That's also been done. And moving to the fine chemicals industry, it's even been used for looking at things like sulfuric acid, which are used in certain chemical processes. So a wide variety of applications where it can extend the detection range of ICP optical emission. Now, I do want to point out additional accessories that can be paired with the U5000 AT+. I did show you a couple of pictures of those actually used in the laboratory. One, of course, is an auto sampler, and the other is a rapid sample introduction system that can also be hooked up between the auto sampler and a nebulizer, be it a conventional nebulizer or an ultrasonic nebulizer. So one that you did see in an earlier picture was the Teledyne CETAC ASX280. This is a compact 2-rack auto sampler. A typical sample capacity. There you see it has 50 ml vials. Those are 21 position racks, so a total of 42 could be placed if you're using those volume samples. 60 position racks are very typical for 15 mil samples, and each rack could hold 60 of those for 120 samples. And then the very common 4-rack auto sampler, which you also saw in an earlier slide, the Teledyne CETAC ASX560. In this case, if you are using 50 ml sample tubes, that's a total of 84 across the 4 racks. And then finally, and this has been the subject of other webinars, some of you may be familiar with this, is the ASXpress Plus, which is a rapid sample injection accessory. In this case, you have a flow injection loop mounted on a valve, and you can use this device to rapidly load up that sample loop and send a discrete volume of sample into your nebulizer system for analysis. The advantages here is that you avoid the longer period of pumping around the peristaltic pump. And certainly you can interface this to a standard nebulizer or to an ultrasonic. This has actually been done for the EN71 method. at a user laboratory. So you can put the appropriate size loop on for your data acquisition, rapidly load it up with the vacuum pump and inject it into the nebulizer system, of course, saving time. So, where to go for more information? Here are the emails for service support if you have an existing system, or sales support if you have questions about acquiring any of these accessories. For technical support, certainly you can contact myself, Fred Smith, directly at fred.smith@teledyne.com, or my colleague Paula Duscott. There's also a lot of information on the Teledyne CETAC website. And here are some links directly to the U5000 AT Plus. This particular application written up, and you can read it at your convenience. Toy safety testing per EN71, and additional information about the auto samplers and also the ASXpress Plus. Okay. So, in summary, when you do use an accessory like this, you are extending the lower range of detection for your ICP optical system. So it can then allow you to do more applications with the ICP-OES, or to be able to meet regulations, especially as regulations may become more stringent. So again, if you have any questions, please send that through the email function for the webinar, and we'll respond as soon as possible. And again, thank you for everyone for attending today's webinar. And that concludes the webinar for today. And I'll turn it then over to Shelley.